Okay, so this is Calculus Section 5, Chapter 3, Section 5. So, I feel like this is a weird section to be in this chapter, but I feel like we've already done these ideas anyway. But let's do them anyway. Let's think about it. It's here, so let's do it. So, what happens to this function, the limit as x approaches infinity, of 5 minus 2 over x squared? Well, so the idea here is we're just thinking, what happens when we plug in like infinity for x? What happens when x is a really big number? And hopefully you did this a bit in pre-calc, but let's just write that down. So I think it is important at least to point out that you can't just plug infinity in for x. Like technically that's not legal. But what you do is you think about plugging in infinity for x. Like if you plugged in a really, really big number for x, like you could even say, I mean, you don't even have to think about it being that big. If it was just like 999. What is 5 divided by 999 squared? Or just what is a number, small number like 5, divided by a really, really big number? The example I always use is if you had one cookie and you were going to break it into a bunch of pieces to split it with everybody in the world, how much cookie would everybody get? Like none, right? Like you'd get no cookie. So, and that's what we do. That's what we say is that when x goes to infinity, 5 divided by infinity is going to be 0, is going to go towards 0. So we just say that that's 0. So when we do this, it's 5 minus 0, which is 5. So the answer is just 5. So these problems are kind of nice. Like, they're kind of nice because they're kind of easy. You see how if you know that rule, there's barely anything to do. We're just taking a long time with it because it's the first one we've seen. We're going to take even longer with it because we're going to look at it on Desmos real quick and just relate to what we just said to what that happens on the graph. Because what we're saying here on the graph is we're saying as x goes to infinity, as the graph goes this way, what is the y value getting closer to? And Desmos tells us it's perfect. Of course, we know it's not. You can see from this view that it's an asymptote, that it's approaching 5, getting closer and closer and closer to 5 as x gets bigger. Which is why the limit as x approaches infinity is 5. So let's keep going. So here we have similar ideas, but let's think about it. So if we had 2 times a really big number, I'm just going to write 2 times infinity minus 1 over infinity plus 1. So the idea is similar here to what it was last time. If we think about the bottom here, infinity plus 1. If we add 1 to infinity, well, for one, we know if we add 1 to infinity, it's still infinity, right? You're taking the biggest number and you're making it bigger. So it's definitely still infinity. But even more than that, does it even matter? I mean, think about how much bigger is this first term, this infinity, than 1? Well, it's literally infinitely times bigger, right? So that 1 doesn't matter if the first thing is infinitely times bigger than it. So when we're looking at this and we're thinking about as x goes to infinity, this 1 is not mattering. And similar on the top, even if we're subtracting it, and that's why, like, if we take infinity and we subtract something from it, well, it is still infinity, actually, because it's still the biggest number. But even more than that, it just doesn't matter. Because if you take 1 compared to infinity, infinity is infinitely times bigger. So this minus 1 is not mattering. But now here, so 2 times infinity, still infinity, right? For sure. But we can't just say now that this is infinity divided by infinity. Because, well, that isn't a determinant case. We are kind of using wishy-washy rules here, which I think are fine. But the way to see this is 2 times infinity. So if you double infinity, that's like infinity plus infinity. Well, that does matter. Because like here we had 1 in infinity, so we said the 1 didn't matter because it was infinitely times bigger. The infinity was infinitely times bigger. But infinity plus infinity, both of those do matter because they're both infinity. So all that to say, we don't just call this infinity over infinity. We call this 2 times infinity over infinity. And we cancel out those infinities just like we would if it was like an x or if it was a number. And look at that. What are we left with now? We're left with 2. So the answer is just 2. And we can see that really quickly if we just look at this and we're like, oh, well, these don't matter. 2x over x, the x's cancel. All you're left with is 2. And of course, remember, they only don't matter when it's infinity. So like, let's look at this graph and let's see how it applies to the graph. How do I pull up the equation bar? Oh, that's right. It's on the bottom over here. That's fine. That's even better. So it was 2x minus 1 divided by x plus 1. So you see it's a rational function. Hopefully you remember the rational function vibe. And so look at your horizontal asymptote. Hopefully you remember that rule just from horizontal functions or rational functions. So look how as x gets bigger, much slower this time than it did last time, but as x is getting bigger, the y value is definitely getting closer and closer to 2. So that's the gist of these. You just think about plugging in infinity. So remember, legally you're not allowed to plug in infinity because infinity is not a number, but you can think about plugging in infinity. So here's just some more limits with more of the same idea. So let's start with the middle one, because the middle one is really the same idea that we had as before. So, just like before, we're thinking about plugging in infinity for x. And so, does that plus 5 or that plus 1 matter? Well, definitely not here, because even more, it's infinity squared. So those definitely don't matter when we plug in infinity. And then just like before we had infinity over infinity and we cancel the infinities. Here we have infinity squared over infinity squared. So we cancel the infinities. And so there's our answer. Our answer is just 2/3. Yeah, we can look at all these quickly in Desmos afterwards too. So let's think about similar ideas for this one. So we're plugging in infinity for x. So just like before, that plus 5 and that plus 1 aren't going to matter. But then now look how we don't have the same thing on the top and the bottom. We have infinity on the top and infinity squared on the bottom. And so honestly, it's going to work the same way that it would if it was an x. One of the infinities is going to cancel. So it's like you're left with 2 over 3 infinity. And now you remember 2, or any number divided by infinity goes to 0 or is equal to 0. Hard to say. I mean, everything we're doing is not totally legal because you're not, like, that's not even a legal thing to write with infinity in there. But it works. It's 0. You just know that 2 divided by a really big number goes towards 0. And so when we're talking about limits, is equal to 0. And so that's what this idea that these are showing. This is showing the other side of it. So we saw when they were equal and they just canceled. What happened when they just canceled? It was just the coefficients. When all of them on the top canceled and just left them on the bottom and ended up being 0 because you've got a number divided by infinity. Now, all the ones on the bottom are going to cancel and just leave you with 1 on the top. Of course, these still don't matter. So then you have 2 times infinity over 3. 2 times infinity divided by any number. That's like with the subtraction we said earlier. It's the biggest number possible. If you divide it by something, it's still the biggest number possible. So that is equal to infinity. So when it canceled out all on the bottom and just left the infinity on top, well, that makes sense, right? Then it ended up being infinity. And now let's glance at Desmos at all these and see how they go. So I can actually just start with that. So let's go ahead and make it exactly what it is. Plus 5 and x squared plus 1. So that's the middle function. And so see how there, as it goes out to the side, the y value, well, if I put the 3 here properly, the y value gets closer and closer to 2/3, or 0.66666. So that's the middle function. That's b. If I make this top exponent smaller, like a, 2x plus 5, so it all just cancels out on the top, only leaves it at the bottom, you see what that does to the graph. Now the end behavior is 0. As x gets bigger, the y value gets closer and closer to 0. Because that was when we ended up with a number divided by infinity. And if we make the power bigger on the top, we make that x cubed now. Now you see what happens. As x gets bigger, the y value just keeps going up and up and up and up and up and up and up. And so you see there, yeah, you zoom out like this, you see the y value is going up towards infinity. Just like we found. So I just think that's nice to glance at. Nice to glance of how the limits that we're finding apply to the graph. And how that's a big purpose of doing limits, I think. Is thinking about limits to infinity and other limits to see like how the graph behaves. Alright, now this one's a fun idea. So it's really the same idea, actually. So we look at this here, and we're just going to say that that plus 1 doesn't matter. Because we're comparing it to infinity. But then now, if we're not caring about that plus 1, now we can like actually simplify that square root, right? It's just the square root of 2, and then the square root of x squared, which is x. So it's like that's our new numerator. And our denominator, we're not caring about the minus 2, because we're plugging in infinity. So we just end up with this situation. And look how, just like before, those x's, or if we plug in infinity, the infinities are going to cancel. And so that just ends up being our answer, 3 over root 2. And so the idea here is like that isn't a square root, so the square root does matter. You just have to, like, you're not allowed to individually square root both of them. But in terms of this, you kind of can think about it like that. But then let's see. So I guess this is what we're really doing. Were any of these to negative infinity and we just missed it? No, all of these were positive infinity. This is our first one we've done to negative infinity. So it's similar ideas. Like really everything at the beginning is still going to be the same. And so we get to here and the x's just cancel. And so we want to do that. But we do have to think a bit more about what's happening with the sign. Because normally when they just cancel, it's like negative infinity over negative infinity. The negatives just cancel. Like the infinities, it's no problem. But here it's not so much the case. Because look how when we plug in negative infinity on top, it's just going to stay negative, right? It's just going to end up being like negative 3 infinity. But when we plug in negative infinity on the bottom, like even though we are canceling it, in reality, with the function, the first thing we're going to do is we're going to square it and make it positive. And then square root it, so it's going to stay positive. And so what that means is that the bottom is going to be a positive infinity, whereas the top is going to stay as the negative infinity. So the infinities will cancel, but it'll end up getting you that, a negative 3 over root 2, as your answer. So let's look at that on the graph, because this is going to have two different end behaviors then, right? So it's going to go to one number on the left and one number on the right. So we've got 3x minus 2 divided by the square root of 2x squared plus 1. Yeah, and so look, here's our graph. On the right side, you see how it gets closer to that. Is that 3 divided by the square root of 2? Square root of 2, 2.12. Getting closer to it. Getting closer to it, yep. But then on the other side, you see how it's negative. It's on the bottom. So that's getting closer to negative 2.12. Very cool. So most graphs that we look at usually have the same behavior on both sides, but they don't have to, and you see the square root here causes that. All right, well, so here, these are fun. So as x approaches infinity of sine of x, so I mean the idea, anytime you're doing as x approaches infinity, the idea is always the same. The idea is you just plug in infinity and think about what happens. So the sine of infinity. What is the sine of infinity? Does sine get closer and closer and closer to a number as x gets bigger? Well, what does the sine graph look like? It just goes like this forever, right? So does this ever get closer and closer and closer to a number? No, it doesn't. It keeps oscillating between -1 and 1. So this limit does not exist. And I think that's a cool reason for a limit to not exist. It just doesn't approach a number. It's not that it's undefined. Like, it is always defined as you go out. It's just that because it oscillates, there's no specific number that it gets closer to. But now this one, on the other hand, is different. Because on the top, the same thing is happening. We plug in infinity, and we get sine of infinity over infinity. And what is sine of infinity? Well, we don't really know. But we know what the sine graph does, right? It goes in between -1 and 1. So we don't know exactly what sine of infinity is. Well, it can't be anything because it goes back and forth. It's not anything, but it's something in between -1 and 1. So we know the top is some number in between -1 and 1. And then we're going to divide it by 0. No, we're going to divide it by infinity. Right? Because it was divided by x, as we're plugging in infinity for x. So we've got some number in between -1 and 1 on the top. We don't know exactly what it is, but in between -1 and 1, divided by infinity. So we've got some number divided by infinity. So what is that? That's 0. It doesn't matter that the top doesn't approach anything specific because we're dividing by infinity. We just need to know that the top approaches some number. And that should be a fun graph. If we look at that graph, we might want to scale it up a little bit to see it better. But yeah, you see what it does is that it goes back and forth, but goes back and forth less and less as time goes on and gets closer and closer and closer to 0. And actually, what it's doing is it's staying in between the 1 over x graph and the -1 over x graph. If you look closely, you can see that it's perfectly bouncing in between those two functions. But that's another thing. That's just what happens when you multiply two functions by each other. But that's another way to see that it does squeeze in between there and asymptotes there at 0. Even though it does go back and forth. Like, that does cross that horizontal asymptote all the time. But it still approaches it as it goes out. All right, now I got a word problem. Suppose that f of t measures the level of oxygen in a pond where f of t equals 1 is the normal unpolluted level and time t is measured in weeks. When t equals 0, organic waste is dumped into the pond, and as the waste material oxidizes, the level of the oxygen in the pond is f of t equals t squared minus t plus 1 over t squared plus 1. What percent of the normal level of oxygen exists in the pond after 1 week, after 2 weeks, after 10 weeks? What is the limit as x approaches infinity? Okay. What percent of normal level of oxygen? Well, normal level is 1, so if it's 90%, it's going to be 0.9. So it's just what decimal? When t equals 0, organic waste is dumped into the pond. As the waste material oxidizes, the level of the oxygen in the pond is oxidizes. So that means getting more oxygen, right? Okay. Well, if the normal level is 1, percent, then like 2 is 100%. Or 2 is 200%, I guess. Well, let's plug in. So what is t measured in? T is measured in weeks. So after 1 week, when t equals 1, and plus we can plug in t equals 0 and see that it starts at 1. When t equals 1, you're going to get 1 squared minus 1, cancels out. So just 1 plus 1 plus 1, so 2. So it goes down to a half. So is it picking up oxygen? Okay, so that's 50%. Because it starts at 1, so just whatever these are, like, that's the percent then. Yeah, as if it gets 2, that's 200%. Yeah. Okay. So you're literally just plugging in. Oh, and you're looking for what it is as time goes to infinity. Okay. Right. So you plug in one, you get 1/2. You plug in 2, that's 4 minus 2 plus 1 over 4 plus 1. So that's 3 over 5. So that's 60%, because that's 0.6. You plug in 10, that's 100 minus 10. Plus 1 over 100 plus 1 is 91 over 101. So whatever that is as a percent, I think there is a trick to do over 101, but I'm not sure. 91 divided by 101? Yeah, it looks like there's a trick, maybe. But basically 90%. And then as t approaches infinity, well, yeah, that's all the tricks we just did. So that's as time goes on. So that's what you should be picturing here, is that the normal level is 1. It starts out at 1, but then organic waste is dumped in. So then it quickly drops down. But then as time eventually goes on, it's going to level out to be 1 again, because all of these are not going to matter. Because I guess we haven't talked about that either. Why does t not matter? Because it's infinity as well. You got infinity squared minus infinity. But the same way how we talked about, if we compare these two, infinity is infinitely times bigger than 1. So the 1 doesn't matter. But then if you compare these two the same way, infinity squared and infinity, well, infinity squared is infinitely times bigger than infinity. So that's why also the infinity doesn't matter. All you worry about is the one with the biggest power. The infinity or the x with the biggest power. So you just have infinity squared over infinity squared. They just cancel. And so as time approaches infinity, it is 100% back to normal. But of course, never actually. It just approaches that. But, of course, again, in nature, these are just models. These aren't what nature exactly has to follow. Nature doesn't follow the rules. Nature just does what they want. So in reality, it probably would go back to normal. It wouldn't be asymptotic. But the best that we can approach it is through asymptotes. So this would be what that graph looks like. So you shouldn't look anything over there. But you see it starts out at 1. They dump the waste in. And it quickly just drops down. Hits its minimum right here at time equals 1. That actually is the minimum. Interesting. But then it rises back up and asymptotes to be back up at 1. Very nice, very nice. Alright, so then we're out of the word problems. So, find each limit. So I guess here, the focus is on infinity versus negative infinity. We had 1 before. This is probably what we should have started with, honestly. So what happens here? We plug in positive infinity. This is not a trick question. It's infinity cubed, which is just positive infinity. What they're getting with is here, that when you do negative infinity cubed, well, the negative works just like you would a normal negative. It's like negative times negative times negative. So it remains negative, but then still infinity. So negative infinity. So that's just your normal rule, that if you cube a negative, it stays negative. If you raise a negative to an odd power, it stays negative. Or if you raise it to an even power, it's going to stay positive. And here we're applying that to this. So same rules as before, only the highest power matters. And then this is going to cancel. And then you're going to plug in positive infinity. So it's going to be 2 times positive infinity. So that's positive infinity. Versus here, I mean, the exact same thing. So let's look at it a couple of ways. Let's do the same thing we did before. You just start the exact same way we did before. And then you plug in negative infinity. But now it's 2 times negative infinity. So, of course, that's negative infinity. So that's correct. Another way you can think about it, just because it's a little fishy, Just like when I first saw this, I'm like, oh, so we're doing negative infinity, but then we're squaring it. So we're going to actually end up with a positive infinity on the top. And that might be true, but if we are going through with that squaring the negative infinity to get the positive infinity, that means that we still have the negative infinity down there. So now we'd be looking at something like infinity squared over negative infinity. So the same thing still applies. You still have infinity and the negative. You still get the negative infinity. So either way you look at it, I think of this as just more of the same. Just more of thinking about what happens when x is really, really big. And that is our last thing from this problem. So that's been the gist of this lesson, what I just said. We're just, for all of these, just thinking about what happens when x gets really, really big. And I just have to say one more time, because of all these incorrect things that I wrote here, all of this notation that I wrote is really not proper. You're technically not allowed to plug in infinity to the function, because infinity is not a number. That is something you should know and be able to say. Infinity is not a number. But in many, many cases, you can treat it like a number. And so that is largely what we took advantage of here.